right? So this is the next question which appeared in 2011 December examination. Okay, just go through the question. The character table of the C2B point group is given below. The two functions phi1 equal to p1 plus 2p2 plus 2p3 plus p4, and another function phi2 equal to 2p1 minus p2 minus p3 and 2p4, where pk meaning p1 p2 p3, right, where pk is the p orbital on kth atom of cis butadiene, and sigma v is the molecular plane here. So this is the molecular plane. We are in our discussion, I have told you, we usually take yz plane as the molecular plane. So sigma v is given as molecular plane here. So this is yz plane. So this should be xz plane. Okay. Yeah, this is given because everybody will get same answer. That's the reason. Okay. Now just go through the question. What they are actually asking, the two function phi1 and phi2. Okay, they are actually molecular orbital functions. Okay, the linear combination of p orbitals forming molecular orbital. Okay, so phi1 is one molecular orbital, phi2 is another molecular orbital. The question is, these two molecular orbitals belongs to, whether they belong to A1 or one A1, another one is A2, like that. We need to identify. Okay, yes, how to identify this, right? Yes, how to proceed. Two molecular orbitals are given. One is phi1 equal to p1 plus 2p2 plus 2p3 plus p4. Okay, just check it. p1 plus 2p2 plus 2p3 plus p4. This is one molecular orbital function. First, we will identify in which irreducible representation this orbital belongs to. Okay, so this is actually molecular orbital of cis butadiene. It is given clearly here. This molecule is cis butadiene. So in cis butadiene, right, we have these four p orbitals. Listen, here this p orbital atom, let me take this as atom 1, this is atom 2, this is atom 3, and this is atom 4. We have 4 atoms, and each carbon atom has a p orbital. But here we have only plus p1, right? Whereas here we have plus 2p2. 2 into p2 means that orbital contribute more. That's the meaning. So let me draw here. So this is p1, and since positive sign is there, I'll put sign of the wave function plus for the upper lobe and minus to the lower lobe. Then second atom has p orbital, which is, I'll draw in larger size because it contribute in larger extent. Again, here also we have plus sign, so I'll put positive lobe above, negative lobe below. Then again here I have plus, and 2 times is there, so I'll put a bigger lobe, plus, minus. And here we have only one p4. Okay, and positive sign is there. So in the fourth carbon atom, you just draw a small p orbital like this, small size. The bigger sides indicate these two p orbital contribute more in the molecular orbital. Smaller size p orbital indicate these two p orbital contribute in lesser extent. That's the meaning. Okay. Now see, this is the principal axis. It is a, all the 4 carbon atoms are in one plane. Cis butadiene. Okay, in which all the carbon atoms are in one plane, and this is the principal axis, right? That is nothing but z axis. Okay, and the entire molecule is in the yz plane. So I'm going to take yz plane. I'll take the y axis here. Y axis passing in the middle. So this is my y axis, and perpendicular axis is x. Now what we have to do? We have to carry out the operations and check whether, so this is p1, right? This is p2, this is p3, and this is p4. Okay, anyway, it's 2p2, 2p3. Don't worry about that. Now we'll carry out the operation, sigma e operation, C2Z operation, sigma V, this is molecular plane, sigma V is given as molecular plane. Here YZ plane is the molecular plane and sigma V XZ is the other plane. When you do identity operation, all the lobes, all the sign remains as such. So I'll put 1. If the sign changes, I'll put -1. Okay. Now, yeah, observe carefully. Listen, I took the first molecular orbital phi1, which is formed by the linear combination of the 4 p orbitals. In that, p orbital of atom 1, carbon atom 1, and p orbital of carbon atom 4, they contribute lesser extent compared to atom 2 and atom 3, where 2p2 and 2p3 contribution is there. Meaning, the p orbital of atom 2, carbon atom 2, and p orbital of carbon atom 3 contribute more, which means you just draw the shape of those p orbital in larger extent. That's all. Now what I'm going to do? I'm going to carry out the operations. See, cis butadiene belongs to C2V point group. In C2V point group, these are the 4 irreducible representations available. Now what I'm going to do? You carry out the operations of C2V point group in this molecule orbital, and check whether sign of the wave function or sign of the lobes changes or not. If the sign changes, you give -1. If sign remains as such, give +1. That's the idea. Now, what is identity operation? Doing nothing. Okay, doing nothing means all the signs, that is upper lobes have positive sign, lower lobes have negative sign, all the sign remains as such. So put +1. Then what is C2Z operation? This is the Z axis. Along Z axis, rotate the orbital by 180 degree. Okay, if I rotate 180 degree, 180 degree means just turning the orbital right in this manner, 180 degree. So if I do like this, what will happen? All the upper lobe will go down and lower lobe will come up. Am I right? When you carry out C2Z operation, okay, if you rotate by 180 degree, what will happen? P4 carbon, that is 4th carbon, will come to carbon 1 place and 1 will go here. They are interchanging the position. And 2nd carbon and 3rd carbon also interchanging the position. When they interchange, what will happen? The p orbital of 4th carbon, it has negative sign in the lower lobe. When you rotate, the negative sign will come to this place and it will go to the upper lobe. It will become upper lobe. So if you carefully analyze all p orbital, right? Now it is get tilted. So all the upper lobes will go down and all the lower lobes will come up. So you will get negative sign in the upper lobe now. So what is happening? Sign of the lobes changing. Therefore, you should give -1. Then what is sigma V XZ plane? Listen, molecular plane is the XZ plane. Remember, all the 4 carbon atoms are in the plane of the paper, but the p orbitals are perpendicular to the paper. Just imagine like that. Now I'm going to keep a plane passing through y-axis and the z-axis. So the plane should pass through all the carbon atom, but it passes through the middle of all the p orbitals. It is passing through the middle of the p orbital. If you do reflection, what will happen? Upper lobe will reflect down and lower lobe will reflect up in all the orbitals. P1 remains in the same position. P4 remains in the same position. P2 remains in the same position. P3 remains in the same position. All the p orbitals remains in their same position, but lower lobe will reflect up and the upper lobe will reflect down because the plane passing through the middle of the p orbitals. So if you do reflection, what will happen? Negative sign will go up and positive sign will come down. Therefore, sign of the wave function changing. So you should give -1. Then what is YZ? XZ plane? X-axis is perpendicular to the paper and this is Z. So you should keep a plane like this. The plane should pass through Z-axis and X-axis. So I am keeping plane like this. Now if you do reflection, these 2 p orbital reflect here and these 2 p orbital will reflect here. P4 will reflect to P1 place and the upper lobe remains as upper lobe. lower lobe remains as lower lobe. Similarly, this will reflect here. So after reflection, if you analyze, the wave function remains, the sign of the wave function remains same. Therefore, there is no change in sign, so you should give +1. Now you see the character table and analyze, okay, which irreducible representation has um, these characters 1, -1, -1, 1. See, 1, -1, -1, 1. Yes, it corresponds to B2 irreducible representation. Okay, so the molecular orbital, the molecular orbital function P1, it belongs to P2 irreducible representation. Take two. Now we'll go to the second molecular orbital P2, which is equal to 2 times P1. So P1 contributes more, minus P2 minus P3 plus 2P4. So here P1, P4 contributes more and they have positive sign in front. Whereas P2, P3 contribute less compared to P1, P4. They contribute less, but they have negative sign. So let me draw the structure here. Observe this carefully. Let me do it here. So P1 is given as 2 times P1 minus P2 minus P3, then plus 2 times P4. Okay, let me draw the structure here. Now in atom 1, this atom 1, this atom 2, this atom 3, this atom 4. In atom 1, this p orbital contributes more. So draw the p orbital in larger size. And since we have positive sign in front, okay, suppose I'll keep upper lobe positive and lower lobe negative. Then in second atom, we have minus sign and the contribution is less compared to P1, compared to atom 1. Therefore, you should draw p orbital in small size, but I have negative sign here which indicates between atom 1 and atom 2 there is a node. See here plus sign. Now sign is changing, right? Plus to minus, which means between P1 and P2 there is a node. So you draw this p orbital in small size. Okay, since there is a node, you give minus sign above and plus sign below. So upper lobe has minus sign here, lower lobe has plus sign. Now here this is minus. See, atom 2 is minus. In atom 3 also we have minus. So sign remains same. That means there is no node between here, between atom 2 and 3. So here I have minus sign. You just keep this as minus and this is plus. Now from P3 to P4, see minus sign, here we have plus sign, so sign is changing. Therefore, and larger contribution, so you give plus sign here and minus sign here. P1, P4, they have larger contribution, okay, and here I have positive sign, here also I have positive sign. Therefore, the P1 and P4 orbital should have a positive sign in the upper lobe. And here I have minus minus, so these two p orbital they have minus sign in the upper lobes. Okay, and as I told before, this is the z-axis which is in the plane of the molecule. Listen, all the carbon atoms are in the plane, but the p orbitals are perpendicular to the plane. Keep that in mind. This is the z-axis. And where is the y-axis? Y-axis is also in the molecular plane. This is y. So y and z are in the molecular plane. X-axis is perpendicular to the plane. Now what I'm going to do, I'm going to carry out the operations. Let me do it here. E C to Z sigma V Y Z. See, Y Z is a molecular plane and it is given in the question paper that sigma V is the molecular plane. So I'm taking sigma V as Y Z. Then sigma V X Z. The question it is given that sigma V is the molecular plane. So sigma V is molecular plane and I represented the molecular plane as YZ plane. So I'm taking sigma V as YZ and next to sigma V or sigma dash V as XZ plane. Okay. Now we should carry out this operation in this molecular orbital and see whether wave function sign change or not. Identity operation doing nothing. So all the signs remains as such. Now you do C to Z operation. Rotation about z-axis by 180 degree. What will happen if I do 180 degree rotation? See, P4 will come to P1 place. P1 will go to P4 place, right? If I rotate like this. P3 orbital will come here. P2 will go here, correct? When you do rotation, what will happen? The lower lobe of P4 will become upper lobe because we are rotating like this. Okay, we see the lower lobe is actually down here. If I rotate by 180 degree, it will come up. It will come up. So this negative sign, if it comes up, okay, so I'll get negative sign here. That means sign is changing. So you give -1 here again. When you do rotation, here the upper lobe has positive sign. But when you do rotation, P4 will come here in such a manner that lower lobe will come to upper lobe, become upper. So here lower lobe is minus. When it become upper lobe, so sign is changing. So give -1. Then what is YZ plane? YZ plane should pass through all the carbon atom and it passes at the middle of all the p orbitals. It is passing at the middle of the p orbitals. If you do reflection, all the p orbital remains in the same position, but upper lobe will reflect down and lower lobe will reflect up. So what will happen? Naturally sign will change. So -1. Then what about XZ plane? X-axis is perpendicular to the paper as I told you before, and this is Z. So if I keep a plane at the middle, P4 will reflect here, P1 will reflect here. When they reflect like this, upper lobe remains upper lobe. This upper lobe remains as upper lobe. So sign of the upper lobes are same. So no changing sign. Similarly here also upper lobes are same sign. So if you do reflection, they interchange their position, but the upper lobes remains as upper lobe, lower lobe remains as lower lobe. So no change in sign. Again, if you analyze these characters in the character table, 1, -1, -1, 1, again it corresponds to B2 irreducible representation. So what does this say? Listen, in this case, both the molecular orbital Phi1, I'm sorry, this is molecular orbital 2, I'm very sorry. Both the molecular orbitals P1 and P2, okay, they belong to B2 irreducible representation. Okay, take note. Yeah, this is the next question. This question appeared in 2013 June. What is the question? Identify the Mulliken notation for the following irreducible representation. Some irreducible representation characters are given here. Okay, characters of the irreducible representation given here. We need to identify what is the Mulliken symbol. Okay, take note. Listen, you just see character of identity operation. Observe carefully. See the character of identity operation. If the character is 1, then the symbol for the irreducible representation either A or B. Remember, A and B are one-dimensional irreducible representations. Suppose if character for the identity operation, if it is 2, then it is two-dimensional irreducible representation, which we represent by the symbol E. If the character is 3, then we use the symbol T or in sometimes F. Okay? So check the character of the identity operation and you can very easily identify the symbols. Okay? So this is rule number 1. Now, either A or B, okay, whether it is A or B, how to check? So listen, this is rule number 2. See the character for the principal axis. See the character for the principal axis. Observe carefully. See the character for the principal axis. If the character of the principal axis, let me write simply Cn. Assume that Cn is the principal axis. If the character of the principal axis is +1, then give the symbol as A. If the character of this principal axis, if it is -1, then give the symbol B. Take note, take note. It's very simple. Rule number 3. Rule number 3. See the character of the vertical plane. Character of the vertical plane. Right? If the character for the vertical plane, if it is +1, then you should give number 1 in subscript. Number 1 in subscript. Okay. If the character of sigma v, if it is -1, then give subscript 2. Observe carefully, right? Listen. So if the character of the reflection operation about vertical plane, if it is +1, then you put number 1 in the right hand side of the symbol, but in subscript. Suppose if vertical plane is absent, okay, if sigma v is absent, observe carefully, this is very important. If sigma v is absent, then you check C2, perpendicular C2. So see the character for C2 which is perpendicular to the principal axis. See the character for the C2 perpendicular to Cn. If this character is +1, then give number 1 in the subscript. If the character for C2 perpendicular to Cn, if it is -1, then give number 2 in the subscript. When we have to use this? If vertical plane is absent, then you can see C2 perpendicular to Cn. Okay, take note. Yeah. Rule number 4. Listen. Suppose if the molecule has inversion or center of symmetry, then see the character of the inversion operation. If the character of the inversion operation, if it is +1, we say that it is symmetric with respect to inversion. If the character of the inversion operation is +1, then you give the symbol as ungerade in the subscript. Ungerade in the subscript. Right hand side subscript. Okay. If the character of the inversion operation, if it is -1, then you give, I'm very sorry, I made a mistake. +1 means gerade, -1 means ungerade. Okay. And gerade, ungerade symbol should be placed in the right hand side subscript. Okay. So don't forget. Then rule number 5. If you have horizontal plane, see the character of the horizontal plane. If it is +1, then you should give a single prime symbol, okay, single prime symbol in the superscript, right hand side superscript. If the character of the horizontal plane, if it is -1, then you give a double prime, right, double prime symbol, right, in the right hand side superscript. Okay, take note. I'll show you how to use these rules to identify the symbol, Mulliken symbol or Mulliken notation for these characters. Okay. Now let me ask you a question. Tell me, what is the character of identity operation here? Character. See here.
1, sir.
A or B.
If the character for identity is 1, then the symbol is either A or B. Okay. Yes, in all the options, A and B are there. Good. To check whether A or B, what to do? To check whether it is A or B, what to do? See the character of the principal axis. Here, Cn is the principal axis. Cn operation. This Cn is the principal axis. So, what is the character of principal axis? +1 or -1? See.
+1.
So A.
+1 means A. Therefore,
A.
yes, the character should be A. Then, is there any vertical plane?
No, sir.
No vertical plane. If vertical plane is absent, what to do? If vertical plane is absent, then C2, yes, perpendicular, yes. Here we have C2, n C2 is there, right? Principal axis is Cn, and there are n C2, which means these are all perpendicular to the principal axis. Okay, and character for C2 axis, see, character for C2 operation is -1 now. -1 means
2,
Two
sir.
subscript.
So you should put number 2 in the subscript. Then next one, see, I is there, inversion, center of symmetry. Okay, listen, character for inversion is -1. Then if character of I is -1, then
Ungerade.
it should be ungerade. So just put u here in the subscript, a to u. Then see the horizontal plane. Horizontal plane is -1. Horizontal plane -1 means
Double prime.
Double slash.
so a to u double prime. This is the Mulliken symbol for these characters or for this irreducible representation. So the correct option for this question is option 2. Am I right? A double prime 2u. So it's very easy, but you should remember the rules. That's very important. Yeah, here I have given a question. You try to identify the Mulliken symbol, okay, for a particular irreducible representation having these characters. Okay, 1, 1, -1, -1, -1, 1. Okay, what is the irreducible? What is the Mulliken symbol?
E1 double prime.
Listen, first step, see the character of the identity operation. Character of the identity operation is 1. What does it indicate? So character of the identity operation is 1, which means the symbol should be either A or B. To check A, to fix whether A or B, see the principal axis. Here this is the principal axis. Character of principal axis is +1. What does it indicate? Yes, you are right. So the correct symbol should be A. Okay. Then is there any vertical plane? See, vertical plane is there. Listen here. So we fix that principal axis is having character +1, so the symbol should be A. Then we have C2 as well as vertical plane. Both are there. When both are there, you should give importance to C2 because C2 comes first in the arrangement of these symmetry operations. It has higher priority. And for C2 operation, character is given as -1. Therefore, you should put 2 in the subscript. Note down. You should put 2 in the subscript because for character of C2 is -1, so you should put 2 in the subscript. Then you go to the next one, horizontal. For horizontal plane, it is given -1, so you should put double prime. So the correct irreducible, the Mulliken symbol for the irreducible representation having these characters is A2 double prime. Take note. Here I have given a question. These are all the characters of some irreducible representation. Find the Mulliken symbol for that irreducible representation having these characters. Yes, just try. Yes, how to proceed? See the character of the identity operation. It is 1. So the symbol could be either A or B. To fix A or B, see the principal axis. Principal axis character is +1, so it should be A. If it is -1, B, but +1 is there, therefore A. Then there is no vertical plane, so we should see the C2. Okay, we should see the C2. I just made a mistake. This is actually 3C2 because the CN axis, so there are 3C2. All these 3C2 axes are perpendicular to the principal axis. Since the vertical plane is absent, so I'm just using C2. Okay, for the character of C2 is -1, which means we should put a double number 2 in the subscript, in the right hand side subscript. Okay, then the next one is inversion. Inversion character is -1, so you should put unjirate, right? Therefore
You.
unjirate. Okay, -1 means unjirate. Okay, take note. This is the Mulliken symbol for the irreducible representation having these characters. Take note. Yeah, I have given another question here. You try to here I have given another question. These are all the operations and their characters are given. You need to identify the Mulliken symbol for the irreducible representation having these characters. Okay, yes, the methodology you know, the identity character is 1, so the symbol should be either A or B. Identity character 1 means symbol should be either A or B. To fix A or B, see the principal axis. If we have only one axis, so it should be the principal axis. Character for the principal axis is 1, so the symbol should be A. Then inversion, listen, inversion is there, therefore you should put inversion character is -1, so you put unjirate, AU. Okay, then horizontal plane is there, which is having -1. So we should put double prime symbol, double prime, right?
Double primes.
Yeah, AU double prime. But take down this. Then see, we have found out that the irreducible representation is AU double prime. Okay, listen, the single prime, double prime. Okay, we put only if the prime symbols are necessary. Suppose if I have single prime, then double prime is necessary. But in the character table, if all irreducible representations have only double prime, okay, or at least if A irreducible representations, right? Irreducible representations having A symbol, if they are only having double prime, then double prime is not necessary. Okay, these are all symbols that we use to distinguish one irreducible representation from the other. Okay, if something is not necessary, you need not consider here. Okay, anyway, for this given character, yes, your answer is correct. Next, now let me move on to the next question. This question, just observe carefully, this question appeared in 2013 December examination. Just go through the question. What they're asking? The transition that is allowed by X polarized light in trans-butadiene is, okay, which transition is allowed by X polarized light, right? So the character table is given for C2H, and 4 options are given. We need to identify which transition is allowed by X polarized light. Okay, how to go with this problem? Listen, we need to identify allowed, X polarized allowed, okay, transition, right? First of all, listen carefully. You know very well, for an electronic transition to be allowed, okay, you should see the spin multiplicity first. Spin selection rule is very important. Spin selection rule. What does this rule says? Spin of the initial state and spin of the final state should be same, or spin multiplicity should be same. Okay, so option A, singlet to singlet, yes, singlet to singlet is allowed, and triplet to triplet is also allowed, triplet to triplet, because same multiplicity. This is what we call as spin selection rule. So singlet to singlet, this is allowed transition as per spin selection rule. This is allowed. Singlet to singlet, yes, this is also allowed. Singlet to single, this is also allowed. See here, triplet to singlet, this is not allowed. So by using spin selection rule, we have identified that this is not possible. Okay, remove it. Then number 2. Now the second selection rule is based on inversion. Listen, also called Laporte selection rule. What does it say? Listen, Gerard to Ungerard or Ungerard to Gerard, these transitions are allowed. Allowed transition. Gerard to Gerard, Ungerard to Ungerard, these transitions are forbidden transitions. So observe carefully here. In option A, I have Ungerard in the initial state and Ungerard in the final state. Ungerard to Ungerard, definitely it is forbidden. Option 2, Ungerard to Gerard, yes, this is allowed. Option 3, Ungerard to Gerard, this is also allowed. So using the Gerard-Ungerard symmetry, we have identified that among the 4 options, okay, 2 and 3 are possible answers. Now, whether 2 or 3, how to fix it? Okay, we'll see the other selection rules. What is that? Listen, you just multiply the character of the initial irreducible representation and final, okay, and see the answer. The answer belongs to some irreducible representation. In that irreducible representation, you see whether X is there or not, because they are asking X polarized light. So what I'm going to do, observe carefully. I'll take option 2. In option 2, I have singlet AU, right? Listen, singlet AU. These are the characters of AU. 1, 1, minus 1, minus 1. So let me write here. The characters are 1, 1, minus 1, minus 1. Then AU to BG. The characters for BG are 1, minus 1, 1, minus 1. So let me write here. Singlet BG. The characters are 1, minus 1, 1, minus 1. Now we should take the direct product. Singlet AU direct product with the singlet BG. So what's the answer? Direct product, just multiply the characters. I'm taking direct product, just multiply the characters. 1, minus 1, minus 1, minus 1 into minus 1 become plus 1. Now see the characters and analyze with the given character table and identify these character corresponds to which irreducible representation. 1, minus 1, minus 1, 1. So it corresponds to BU. 1, minus 1, minus 1, 1 corresponds to BU. Along BU, I have X as well as Y. I have X as well as Y. Therefore, observe carefully. After taking direct product, we got some character. These characters, if you analyze with the character table, these characters belong to BU. Okay, I'll just put singlet BU. It belongs to singlet BU. Then along BU, see this area, I have both X as well as Y. So here we have X. Here we have X. Yes, if we pass X polarized light, yes, this transition singlet AU to singlet BG transition will be allowed as per group theory. Okay, so this is allowed. It is X polarized allowed. What about this? Let me check it out. BU and BG. So I'll take BU. For BU, the characters are, let me write in the next page. Yeah, I'll write here. For BU, the characters are BU. Characters are 1, minus 1, minus 1, 1. BU, characters of BU. Then characters of BG, singlet BG. BG, the characters are 1, minus 1, 1, minus 1. 1, minus 1, 1, minus 1. Now take the direct product of BU into BG. Direct product, just multiply 1 plus 1 minus 1 minus 1. Now just analyze the character table and identify which irreducible representation has these characters. 1, 1, minus 1, minus 1. 1, 1, minus 1, minus 1. Yes, it is AU. Okay, it is AU. But in AU, along AU, if you analyze this area, I have only Z. So this transition, singlet BU to singlet BG transition is Z polarized allowed. But in the question they are asking which transition is X polarized allowed? Yes. Yes, only option 2, that is singlet AU to singlet BG. This transition is allowed by X polarized light. Okay, so the correct option for this question is option 2. Take down. See this question appeared in 2014 June. The result of the product C2X into C2Y is. Okay, they are asking the result of the product. Listen, C2 operations are given here. Whenever C2 is given, only C2, right? This is C2, this is also C2. You can use, okay, a single point, right, and carry out the operation. Suppose you take a point in Cartesian coordinate space. Say for example, I'll take some point having X value X1, Y value Y1, Z value Z1, X1, Y1, Z1. Okay, this is some point in Cartesian coordinate space. Okay, now what I'm going to do, we should carry out these operations. I have already told you, always if product of two operations are given, you have to do the second operation first. So C2Y. So I'm going to carry out C2Y operation. What is meant by C2Y? Along y-axis you should rotate by 180 degree. So this is y-axis, y1. y1 corresponds to y-axis, right? Now if I rotate by y-axis, what will happen? The y1 remains as such. I am rotating along y-axis by 180 degree. So y1 value remains as such. X1, Z1, they go to exactly opposite side. So what is meant by that? It becomes like this. X1 become minus X1, z1 become minus z1 because I'm rotating along y-axis. Y doesn't change. X and y goes to exactly the opposite side. Okay. This is after C2y we get this result. Now what we have to do? After C2y you should carry out another operation along the x-axis. Okay. In the product, this is the result. In the result I'm applying C2x. So now I'm going to rotate along x-axis. So x remains as such. X1 minus x1 remains as such. Now since I am rotating along x-axis, y1 become minus y1. Okay. And z1 minus z1 become plus z1. Plus z1. So this is the result of these two multiplication operations. C2y into C2x. This multiplication, this product operation will give me this result. Now what I have to do to get this directly? Can anyone tell me? Which operation I have
C2
to
is
perform? C2? Yeah.
sir.
If you analyze, very good. If you analyze these points, listen. See, z1 remains as such, plus z1 plus z1. x1, y1 sign changes. That means you should rotate this along z-axis. If you rotate along z-axis, z remains as such, x and y changes sign. Okay? And we are rotating by 180 degree, so they go exactly opposite side. That is the reason why they change sign. Okay? Therefore, the correct option among these is option 3. Right? Take 2. This question appeared in 2015 June. The question is this. The product of C2 along x-axis into sigma xy. C2 along x is the two-fold rotation axis around x-axis, and sigma xy is the xy mirror plane. What is the product of these two? Listen, since C2 is given and sigma xy is given, you can use a single point. Okay, and you can analyze very easily. Listen, how to do that. So let me take a point here. Say initially a point has x value x1, y value y1, and z value z1. This is the initial position of a point in Cartesian coordinate space. Now what I'm going to do? I'm going to carry out this product operation. In the product, always do the second operation first. So I'm going to keep a plane. I'm going to keep a plane passing through x and y. If we keep a plane passing through x and y, then x value, y value remains as such. They do not change. Whereas if you do reflection in xy plane, z becomes minus z because you are reflecting. So it goes to the exactly opposite side. So it becomes minus z1. Then, so we finished sigma xy operation. We got some result. Now for the result, you apply C2x operation. C2 is given like this, meaning you have to rotate along x-axis by 180 degree. If you do rotation by 180 degree along x-axis, x remains as such, whereas y1 z1 changes sign. So y1 become minus y1 and z1 become plus z1. So I got some result which is nothing but the product of these two operations. This result is due to the product of these two operations. Now tell me how to get this directly from initial one. Which operation will give this? Yes. So here if you analyze this and this, it is very clear that x1 remains as such, z1 remains as such, but for y1 sign is changing, which means you should keep a plane passing through x and z. X and z. If you keep a plane passing through x and z, x value, z value remains as such, y changes sign. So the product of these two, that is sigma C2x into sigma xy, this product is equal to sigma xz operation. So the correct option for this question is option 1. Take down. Yeah, the next question is this. This question appeared in 2016 June. D3 point group character table is given. for this point group, the correct statement among the following is, 4 statements are given. You need to identify the correct one. Okay, just go through the statements first. Listen. So just go through the statement 1. It is given that it is possible to have a totally symmetric normal mode of vibration which is IR active. Listen, totally symmetric means, listen, all the values should be +1. Yes, in this character table, A1 irreducible representation is totally symmetric. But in totally symmetric irreducible representation, in the area 3, there is no X, there is no Y, there is no Z in area 3. Which means if any normal mode of vibration belongs to A1, it cannot be active in IR. It is IR inactive, but it is given IR active. Therefore, this statement is a wrong statement. It should be IR inactive because there is no X, no Y, no Z. Now, let me move on to statement number 2. All IR active normal modes are necessarily Raman inactive. All IR active necessarily Raman inactive. There is no inversion. See, observe carefully. Is there any inversion present? No. If inversion is there, you can say comfortably that mutual exclusion principle become valid. So vibrations which are IR active, are not active in Raman. Similarly, vibrations which are Raman active, they are not active in IR. This is possible only if centrosymmetries exist. But here there is no centrosymmetry, and they are saying that all IR active normal modes are necessarily Raman inactive. No, this is also wrong statement. IR active normal mode can also be Raman active. Okay, centrosymmetry is not there. Now let me move on to third option. Third statement. All Raman active normal modes are necessarily IR active. All Raman active normal modes are necessarily IR active. You can easily answer this question by analyzing the character table. In the character table, see, A1 irreducible representation, they have Z square term. It has Z square term. Therefore, this is Raman active. A1 is Raman active. Okay, but there is no XYZ, so it is not IR active. So Raman active vibrations need not be IR active. Similarly here, see A2, along A2 there is no binary coordinates. So it is A2 vibration is Raman inactive, but it has Z here. So it is IR active. So this statement is also wrong. Why? All Raman active normal modes are necessarily IR active. No, this is Raman active, but it is IR inactive. Okay, so this statement also a wrong statement. See statement number 4. It is possible to have a pair of IR active normal modes that are degenerate. Yes, this is correct. Why? Because I have a two-dimensional irreducible representation. Two-dimensional irreducible representation is there, and listen, there is a possibility that if sometime, okay, two normal modes, right, may belong to the same irreducible representation E. We call them as doubly degenerate. 3 irreducible representation, right? 4. So usually in this point group, 2 normal modes can present in same irreducible. So it is possible to have a pair. Yes, it is possible. Why? Because I have, if all are one dimension, then only one normal mode is possible for a particular irreducible representation. But I have a two-dimensional irreducible representation here. This, see, A are one dimension, E is two dimension. Two-dimensional irreducible representation is there. Therefore, a pair of normal mode, okay, or maybe may exist in this irreducible representation. Okay, yes, the correct statement for this question is statement 4. Take note. This question appeared in 2016 December. The question is this: the pair of symmetry point groups that are associated with only polar molecules. Only polar molecules. So
Okay, sir.
yeah. So which are all the point groups belong to, or which polar molecules? Polar molecules belongs to, remember, polar molecules belong to Cn, Cnv and Cs point group. Then you should include C infinity V also. If molecule belong to these 4 point groups, then they are polar molecules. Okay, they are polar molecules. So in option A, C2V is polar, but D infinity H, there is a center of symmetry available, so it cannot be polar. Here C3V is okay, but in C2H there is a center of symmetry, so it cannot be polar. Molecule belong to C2H cannot be polar. Then here D2H, it has center of symmetry, it cannot be polar. Tetrahedral, perfectly symmetric molecule, cannot be polar. C2V and C infinity V, yes, both these point groups, okay, they do not have center of symmetry and they are low symmetric. Sorry, they have dipole moment. Okay, say for example, water molecule, yes, it is polar. It belongs to C2V point group. You take HCl. HCl molecule, it is polar, belong to C infinity V point group. So polar molecules belong to Cn, Cnv, Cs and C infinity V point groups. Take note. So the correct option for this question is option 4. Yeah, this question appeared in 2017 June. The question is this: for a point group, an incomplete character table is given below. Some incomplete, A1 is there, A is there, something is not there. Given below with one irreducible representation missing. Right? We need to identify this missing irreducible representation. I didn't give the options here. Okay, you yourself try and tell me what could be the answer. Yeah, listen. See, in this character table, there are 3 classes. There are 3 classes, so there should be 3 irreducible representation. Okay, this is very important. Number of classes is equal to number of irreducible representation. Then what is the order of this group? 3 plus 2, 5, 5 plus 1, 6. So order of the group is 6. Okay, remember, if you take the squares of the dimensions, right? Take the squares of the, L is the symbol we use for dimension. Take the squares of the dimensions of each irreducible representation and sum it up. You should get the value should be equal to order of the group. So listen carefully. This irreducible representation A1 means one dimension. Dimension is 1. So 1 square plus, for second irreducible representation, we don't know what is this. So let me put simply x square plus third one, identity E is there. E means 2 dimension. So 2 means 2 square. This should be equal to 6. Order of the group is 6. Okay, can anyone tell me what is the possible value of x?
No, sir.
Yeah, listen what I did. Listen, these are the dimensions. Okay, dimension for A1 is 1 dimension and this is 2 dimension. And for the middle one, this number we don't know. So what I did, I just applied the rules. Okay, sum of the squares of the dimensions of all the irreducible representation should be equal to the order of the group. So here dimension is 1, here dimension is 2, here we don't know what's the dimension, let it be x. Take the square, 1 square plus x square plus 2 square, 1 square plus x square plus 2 square, that should be equal to order of the group. Order of the group is 6. So we found out x is equal to plus 1 or minus 1. Since x indicate dimension here, dimension cannot be negative. So the second irreducible representation should be a one-dimensional. That's why I put 1 here. Now you need to identify the remaining 2 boxes. Okay, how to identify? Listen, it's very simple actually. How to proceed? Listen. Try to remember this formula. It's very important. I'm going to use orthogonal condition now. I'm going to use orthogonal. Listen, A1 and this irreducible, we don't know what is this. A1 and this irreducible, let me use this symbol gamma. A1 and gamma, these two irreducible representations must be orthogonal. Okay, must be orthogonal. Listen, what is the formula? The formula is this: summation. Okay, summation, number of operations in each class. So let me write GR. GR is the number of operation in each class into character of the ith irreducible representation in the class R into character of the jth irreducible representation in the class R. This product should be equal to 0, then only they are orthogonal. Now I'll take A1 and A1 irreducible representation and gamma. I'm going to check whether these two orthogonal or not. It should be orthogonal, it should be. Okay, but now I'm going to fix that. Now I'll take class 1. In class 1, I have one identity operation. So 1 into character for A1 is 1 and character for this irreducible representation is also 1 for class 1 plus class 2. Let me go on to class 2. In class 2, I have two operations here, 2 into 1 A1 character, and we don't know what is the A2 character, let it be A, plus similarly here 3 into 1 into B. I'll take this as B. That should be equal to 0. Okay, so here I'll get 1 plus 2A plus 3B equal to 0, or I can write 2A plus 3B equal to minus 1. Okay, I'm just using the orthogonal condition here. Then similarly, this gamma must be orthogonal to E. So gamma and E must also be orthogonal. Okay, right? So if you use the same rule here, right? Number of operation in class 1 is 1 into 1 into 2 for class 1 plus for class 2, 2 into, and for this let me take the value as A into minus 1 plus 3 into B into 0. This sum should be equal to 0 because they are orthogonal. So what we get, 2 minus 2A, this is 0 equal to 0. Therefore, I'll bring this minus 2A to this side. So 2 is equal to 2A or A is equal to 1. We found out the value of A. See, in this character table, I took this as A and this character as B. We found out the character of A, which is nothing but 1. And what is the character of B? Substitute this A is equal to 1 here. If I substitute this A, what will happen? See, 2 into, in the place of A, you put 1 plus 3B equal to minus 1. 1 into 2 is 2 plus 3B equal to minus 1. Bring the 2 to the right hand side. I'm sorry, this is 3. Bring the 2 to the right hand side, you'll get minus 2. So 3B equal to minus 3 or B equal to minus 1. Okay, so this character, right? So the irreducible representation gamma has the character 1, 1, minus 1. Okay, A value 1, B value minus 1, and these are the characters. Okay, take down. These are the characters. Now, can anyone tell me what is the symbol for the, what is the Mulliken symbol for this irreducible representation? Identity character is 1, so the symbol should be either A or B. To fix A or B, see the principal axis. Principal axis character is 1, so it should be A. Then vertical plane, yes, it is given minus 1, so it should be A2. A2, take down. See, some normal mode as the symbol E for their first excited state. Listen, for a normal mode, for a particular normal mode, okay, there are ground vibrational state, first excited vibrational state, second vibrational state. There are many excited states that are available. Okay, to identify, see, now we don't know what is the ground state of the normal mode, but for the first excited state, the symbol is given. For the first excited state, irreducible representation symbol is given. Listen carefully. For the ground state always totally symmetric irreducible representation is the symbol. Totally symmetric irreducible representation should be the ground state symbol. These are all symbols of the wave function. Ground state wave function belong to this symmetry. So which is totally symmetric for C3V character table? A1, correct? Am I right?
Yes, sir.
A1, take note. Listen, very simple. Keep this in mind. We don't know what is the ground the ground state or the in which irreducible representation the normal mode belong. That we don't know. Okay, you find the you should know this actually, but it is not given. Right, irreducible representation of the normal mode is not given. Power, the vibrational quantum number V will give you characters, and using that character you just analyze the character table and identify the irreducible representation. Okay, observe carefully. Now we don't know this, we don't know. So first you keep this one as such. If you put 0, you will get the ground state characters. Okay, whatever may be the number, see this irreducible representation we don't know. Okay, so whatever may be the characters, if you put power 0, okay, to 1 power 0, 2 power 0, something, anything power 0 is 1. So always I'll get 1, 1, 1. 1, 1, 1 means it should belong to totally symmetric. Yes, for C3 point groups, totally symmetric is A1. So ground state, if we put V equal 0, I'll get ground state. Ground state must belong to totally symmetric. Then what about the first excited state? You take the same irreducible representation of the normal mode and you should put 1. If I put 1, listen, something power 1, something power 1, something power 1, that should give me E. What is the character for E? Can anyone tell me what is the character for E in the table? In C3V table? 2
minus 1 0.
2 minus 1 0. If I put, listen, if I put power 1 1 1, it means it gives you the irreducible representation for the first excited state. Okay, listen, power 1 means 2 minus 1 0. I'm going to say 2 minus 1 0 corresponds to E. Observe carefully, right? Observe carefully. Listen, for the first excited vibrational state, the irreducible representation is nothing but the irreducible representation for the normal mode. I repeat, this is very important rule. Keep this in mind. Very important point. Then irreducible representation of the normal mode is equal to irreducible representation of V equal to 1 state. That is first excited vibrational state. Irreducible representation of the first excited vibrational state is equal to the irreducible representation of the normal mode. And in this problem, this is given as E. Therefore, the normal mode irreducible representation is also E. Now you put E power 2, you will get the irreducible representation. So E power 2, listen, E characters are 2 minus 1 0. You take the square. If you take the square, I'll get 4 1 0. 4 1 0 are the characters. Now in which irreducible representation they belong? Listen, this is actually reducible, correct? So let me find out whether A1 is there or not. A1 here order of the group is 6 into number of class 1. In class 1, number of identity operations is 1, and reducible character is 4. Along A1, the character is 1 plus second class. In second class, we have 2 C3 operations. So 2 into character is 1 here, and irreducible character along A1. A1 is totally symmetric, so all characters are 1. And here I have 0, so you need not find the last one. 4 plus 2, 6, I'll get 1A1. So this contains 1A1 irreducible representation. Okay. Then you find out A2, right? 1 by 6, 1 into 4 into 1 plus 2 into 1 into along A2 second class. What's the character along A2? Class 2 character. 1 or minus 1? 1, right? 1 plus. Since this is 0, you need not calculate. So 4, this is 4, this is 2, 4 plus 2, 6, 6 by 6 is 1. So I am getting 1A2 also. What does this indicate? Listen carefully. I should get the characters 410, right? Now let me do it in the next page. Just copy down. Now we found out two irreducible representation, A1 and A2. Okay, what are the characters of A1? 1, 1, 1. What are the characters of A2? 1, 1, minus 1. We know that. Now we should introduce another irreducible representation so that the sum should be equal to 410. Sum should be equal to 410. Okay, without reduction, I am going to give the answer. So 2 minus 1, 0. If I put 2 minus 1, 0, these are the characters of E. Add them. If you add, you will get 4, 1, 0. Am I right? Am I right? Therefore, the second excited state, right? Irreducible representation corresponds to V equal to 2 state. V equal to 2 state, right? Is equal to A1 plus A2 plus E. It is the sum of all the three. Take note.